Popular culture is often fascinated by the concept of acids and bases. From acid alien blood to large vats of acid, people's conception of what acids and bases do is reinforced by popular media. However, very rarely are these depictions accurate. Bases are generally more corrosive than acids, which is why you would drink a highly acidic soda, but you wouldn't drink bleach, which is a strong base. Let's spend some time breaking through the mystery of acids and bases and see how they relate to the equilibrium constants and chemical properties of water. Previously, we have looked at the simple systems of strong acids and strong bases. These are ionic compounds that completely dissociate and react to form water and a salt. Make sure you refresh your memory of which acids and bases are considered strong. With these, we defined acids as proton donors and we defined bases as proton acceptors. This is the Bronsted-Lowry definition. There are other ways to define acids and bases. Arrhenius takes the opposite approach and defines bases as hydroxide producers and acids as hydroxide acceptors. Finally, Lewis, that guy from Lewis structures, defined acids as electron pair acceptors and bases as electron pair donors. These are all different ways of looking at the same process. The focus here is on the creation of protons and hydroxide ions in solution. What is interesting is that water is amphoteric, which means that it acts like an acid and a base all by itself. Let's visualize this as a reversible reaction, an equilibrium, if you will, between water and the ionized form of itself. Hydrogen protons generally don't stay loose in solution, so they produce what is called the hydronium ion, H3O+. This process is happening in water in equilibrium at 25 degrees Celsius with a very small K value of 1 × 10⁻14. This process is temperature dependent and endothermic, so we get more ionization at higher temperatures. We can set up the equilibrium relationship for this reaction where the K of water equals the hydronium ion concentration times the hydroxide ion concentration. Why isn't there a denominator in this equation? Right, because liquids don't figure into the equilibrium constants. So, we can relate the concentration of hydronium ion to hydroxide ion using this equation. Notice that because there is no denominator, the exponents always add up to -14. Wouldn't it be a lot easier if we could just eliminate all the mess and talk about the numbers just using the exponents? Well, we're in luck. A great way to express concentrations that span large exponent ranges is to use a logarithmic scale. We can do this with any type of system using the generic equation px equals the negative log of x. This is where the concept of pH comes from. So pH would equal the negative log of the hydronium ion concentration, and pOH would be the negative log of the hydroxide ion concentration. Notice that these values sum up to 14, as we would expect based on the exponent analysis and the equilibrium equation. We can calculate the pH or pOH of strong acid or base solutions using what we already know. Imagine that we have a solution of 0.67 molar lithium hydroxide. Lithium hydroxide is a strong base. The dissociation equation tells us that there is a 1-to-1 molar ratio between the hydroxide concentration and the starting concentration. Thus, we have a 0.67 molar concentration of hydroxide ions in the solution. We can plug that into our pOH equation and get a pOH of 0.17. What is the pH of this solution? We can just subtract 0.17 from 14 and get the pH of 13.83. We can also use the pH and pOH to determine the concentrations of hydronium and hydroxide ions. If a solution has a pH of 5.67, what are the hydronium and hydroxide ion concentrations? So 5.67 equals the negative log of the hydronium ion concentration. We can move the negative sign, take the inverse log of both sides, and we get 2.1 × 10⁻⁶ molar. To get the hydroxide ion concentration, we can subtract the pH from 14 to get the pOH. Then use that the same way to calculate the hydroxide ion concentration. We get 4.7 × 10⁻⁹ molar. Read and work through pages 101 through 108 in your workbook. Weak acids and bases. So, what happens when an acid or base is weak? The simple answer is that they dissociate in an equilibrium. The dissociation of a generic weak acid would look like this. A Ka for a weak acid has the equation product concentration over reactant concentration. We have been using the hydronium ion thus far, but we can also simplify it to H+, as long as we realize that these protons are not just floating around in solution unbound. In this equation, A- is what we would call a conjugate base, because it can accept a proton as part of the reverse reaction. It is an important concept that weak acids and bases produce conjugate bases and acids as products, which can then act like weak bases and acids in the reverse direction. The larger the Ka, the stronger the acid. The Ka for a strong acid would be something on the order of 1,000,000. So weak acids would fall well below that. In the same way that we can calculate a pH, we can also calculate a pKa. The smaller a pKa value, the stronger the acid. Let's calculate the pH of a 0.317 molar solution of hydrogen cyanide. Hydrogen cyanide has a Ka of 4.9 times 10 to the minus 10, and thus is a weak acid. So we can set up an ice table. The balanced dissociation equation sets up our ice table columns. We know that the concentration of hydrogen cyanide is initially 0.317 molar. The Ka equation can be used to solve for the change in concentration, or X. X is also the final proton concentration. We set up the Ka equation and solve for X using the quadratic equation. Thus, the proton concentration is 1.25 times 10 to the minus 5th molar. We use that to get the pH, which turns out to be 4.9. Weak bases follow basically the same rules. We just have to be careful to note whether we have a POH or pH and calculate accordingly. For a weak base, we have Kb and pKb. Let's look at how this works. Cocaine is a weak base. A 0.001 molar solution of cocaine has a pH of 9.7. What is the Kb for cocaine? From the pH, we can calculate the POH of 4.3, which gives us the equilibrium concentration of hydroxide ions using POH equals a negative log of the hydroxide ion concentration. So 5 times 10 to the minus 5th molar. We can set up an ice table for this reaction. We can calculate X. Then we can finish filling in the table. So we can set up the Kb equation, plug in what we know, and solve for Kb, which comes out to 2.6 times 10 to the minus 6. Read and work through pages 109 through 112 in your workbook. Salts. Sometimes, weak acids and bases can be hiding in a salt or ionic compound. Consider the polyatomic ions that we have memorized previously. Most of the anions on this list are actually weak acids in disguise. Remember that one of the definitions of an acid is a proton donor, and bases are proton acceptors. If we look at acetate, C2H3O2-, we can see that it would accept a proton and form acetic acid, which is a weak acid. Additionally, when we look at the equation for this weak acid, we see that the acetate is the conjugate weak base because it can pick up a new proton and form acetic acid. Now, consider sodium acetate. We can draw a dissociation reaction for this salt, and we get sodium plus the acetate. Sodium is the conjugate for a strong base like sodium hydroxide, so it will act like a spectator ion and not attach to anything in solution. It's basically 100% soluble in this context. However, the acetate has the potential to grab a proton from water and produce hydroxide. So, it will act like a weak base. The equation for this weak base reaction would look like this. Appendix F in your workbook has a table of weak acids. This is not an all-inclusive list, so you won't be expected to memorize it. However, you should be able to use this table to answer questions that you might encounter. Let's look at a couple of examples and see how to identify conjugate acids and bases when they are hiding in a salt. Let's take lithium nitrate. We need to decide if there is a conjugate acid or base hiding in there somewhere. Any component of a strong acid or base becomes a spectator ion in solution. Since lithium is part of lithium hydroxide, a strong base, then it is only a spectator. Nitrate is actually part of nitric acid, a strong acid. Thus, it also acts like a spectator ion in solution. Lithium nitrate is thus neutral. What about sodium hypoiodate? Again, sodium is a component of sodium hydroxide, a strong base. Thus, it acts like a spectator ion. However, hypoiodate is the conjugate base of hypoiodous acid. Thus, it will pick up protons from water and form hydroxide ions in an equilibrium following this equation. Last, let's look at hydrazine perchlorate. In this molecule, perchlorate is the spectator ion, but hydrazine is the conjugate acid of a weak base, so it can give up protons in solution according to this equation. Read and work through pages 113 through 115 in your workbook. We can use these acid or base equilibriums to solve for the pH or equilibrium concentrations using the methods we have seen before. Let's try one. What is the pH of a 0.2 molar solution of lithium acetate? First, we decide if we have a hidden conjugate acid or base. Lithium is part of a strong base, lithium hydroxide, so it's a spectator. However, acetate is the conjugate base of acetic acid. Thus, we get this equilibrium reaction. We find the Ka of acetic acid, and since this is the conjugate base, we can use Kw to solve for the Kb. Now, we need to know the hydroxide ion concentration to get the pOH, and use that to get the pH. We can create an ice table. We know the initial concentrations and the Kb. We can solve for the change in concentration and we get 1.1 times 10 to the minus 5 molar. X is our final hydroxide ion concentration, so we can use that to get a pOH. Then we can subtract that from 14 to get our pH value. Read and work through pages 116 through 118 in your workbook. Next, we'll take a look at some acid-base reactions and use what we know about equilibrium to solve some more problems.